All right, so let's start.
All right, hi. This is our Elementary Physics 1 group project. We did it over Newton's third law of motion, and it's by Haley O'Brien, Lashiri,
Erica Robinson.
Amy Lowe.
And this is Zainab.
Okay. All right, so a little introduction. Centuries ago, Sir Isaac Newton defined three laws of motion. The development of Newton's three laws of motion mark a transition from the Renaissance to the modern era of science, where scientists started debating the nature of the universe and straying from their logical ways. The discovery of these laws is arguably the most pivotal point in the history of physics. This presentation will discuss Newton's third law of motion, which states that for every action there is an equal and opposite reaction. In simpler terms, whenever one body exerts a force on the second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that the first body exerts. This law highlights the interaction between objects and is crucial in understanding the principles of motion, force, and how nature works. So some relevant fields that are affected by Newton's third law, the main one is mechanical engineering. When designing a structure or model, engineers use Newton's third law to ensure that their designs are balanced. An example of this being used is in 1990, the Tower of Pisa, or in the 1990s, the Tower of Pisa was reaching a dangerous level of tilt. The engineers needed to act fast and decided on lead counterweights, so they would place over 450 tons of lead counterweights on one side of the tower, hoping that it would pull the opposite side and effectively reduce the tilt. Newton's third law was being exercised in this case, and the action would be placing the weights, and the equal and opposite reaction was the decrease in tilt. So the main obvious relevant scientist would be Isaac Newton. A quick biography of him: he was born in 1642 and he died in 1727. He was born a Puritan in Lincolnshire. After a rough childhood, he started a study at Cambridge University, which would prove to make him quite an authority in London. He sparked the onset of one of the most influential scientists to ever lived. Newton is the most known for his discovery of gravity. However, he also discovered calculus, which helped solve complex math problems. He discovered the color spectrum with a glass prism, and finally his three laws of motion, which changed physics forever. And a little fun fact about him is that he almost blinded himself by staring at a reflection of the sun in a dark room while trying to observe light. And then someone who helped him along the way was Galileo. He was born in 1564 in Italy, and he would go on to study at the University of Pisa, where, despite his father's wishes, he would study physics. He studied the great Aristotle's work and questioned it. The subsequent testing of Aristotle's work is what Galileo is most remembered for. Aristotle claimed that the heavier the object was, the faster it would fall, and Galileo proved him wrong through testing. He discovers that objects fall in frame, and he would go on to study movement and force, which would lay the foundation for Newton to develop the three laws of motion. And an interesting fact about him is that he was never married, but he did have 3 children with a woman named Marina Gamba. Okay, the original experimental process, unlike the first and second laws, Newton developed the third law of motion through observation and reasoning rather than experimentation. He actually used his first 2 laws to help him with the discovery of the third law. The first law of motion states that a body at rest remains at rest, or if it's in motion, it remains at a constant velocity unless acted upon by a net external force, also known as the law of inertia. After studying said force, he revealed that there will always be an equal and opposite reaction to it. This is now recognized as Newton's third law of motion. He was born the year after Galileo, so they never actually interacted, but he would go on to use Galileo's research to uncover his laws of motion. Galileo's theory of inertia and experiments on free fall demonstrated that force is necessary to change on objects' state of motion, and that these changes are always due to interactions between objects. So although they never existed on the planet at the same time, they made history together and defined the laws of physics. Although no famous experiments were performed, like the famous apple falling on the head and everything, the discovery of the third law of motion, Newton did create the cradle, which is a display. So like after he discovered the law, he created the cradle, which is what proved his law. And you can see on the right is a picture of the cradle.
The initial hurdles, dominance of Aristotelian physics. During the time Newton was proposing these ideas, Aristotle was the kind of science. Newton's new theory suggested that forces act in pairs, which directly contradicted Aristotle in his studies. However, Newton overcame this and sparked the start of modern era for science. Limited tools for measurement. Motion and speed are visible and can easily be measured. Force, however, is hard to define by a number, especially in Newton's time where technology was not as advanced as today. This may have made his argument to Aristotle's theory unreasonable. Misinterpretation, because Newton did define so many things we know about physics today, he didn't have much to rely on in order to understand something. He had to learn everything about it, which was likely extremely frustrating. This could lead to misinterpretation and in turn trial and error. Why even bother? Fascination. Like many other brilliant people, Isaac Newton was obsessive. He was fascinated with motion and why things moved. The story goes that he was sitting under an apple tree, and when an apple fell on his head, he started to wonder why. That question sparked investigation, more questioning, and the eventual defining of the three laws of motion. This, along with the motivation of great scientists like Galileo's research, Newton was inspired to get to the bottom of why movement takes place. Finally, Newton wanted to prove once and for all his theory that the same rules apply for all things, whether on the ground, in the air, or in outer space. Immediate effects. The development and spread of Newton's laws of motion changed scientists' point of view on everything. At the time, most scientists were thinking very logically and relied on observation and physical evidence for their studies. Newton's emphasis on forces that cannot be seen is what changed the perspective of many and ultimately sparked the modern era of science. Newton's breakthrough also changed way the celestial realm was viewed. Newton's great insight was that the same laws that govern the motion of objects on Earth also govern objects in the solar system and beyond. No longer would the heavens be regarded as mysterious bodies moved by unseen hands, but as real objects that obey the same laws of physics we do here on Earth.
The modern process, there are a lot of ways to experiment Newton's third law in modern day. You can do many like simple experiments, just one being a balloon being propelled into the air by letting it go. After filling it with air, it would demonstrate the reaction force of the air being propelled. Another one could be just swimming. When a swimmer pushes against the water with their arms and legs, the water pushes back and the swimmer is propelled forward. Many things we do in day-to-day life can be used to demonstrate Newton's third law. And then just some differences. Modern techniques differ from traditional techniques, mainly in the technology and tools used for measurement and analysis. The traditional methods relied really on visual observation, simple calculations, and lacked precise control over experimental conditions. It made it really difficult to get an accurate read on the experiment. But in modern day, we have high quality force sensors, sophisticated software, and the motion capture systems. It makes it a lot easier to get a specific and accurate answer to the experiment. And then just some benefits. Modern benefits of Newton's third law are found in engineering, technology, and everyday applications. One example would be rocket science. Modern rocket designs rely heavily on the law. Rockets expel exhaust gases downward, which propels the rocket upward. Action and reaction, which is the key point of Newton's third law. A more common one would be vehicle design. Car designs use Newton's third law to optimize traction and movement. When cars' wheels exert a backward force on the road exerts equal and opposite reaction, and propels the car forward. And then in the future, it's going to help scientists explore many fields of research: quantum and nanoscale applications, space propulsion, technologies, robotics, and aerospace engineering, and energy harvesting. Those are just a few things that Newton's third law is going to help us discover one day.
All right. Objective 4.1, we chose this question, and I would like to tell that why did we choose this question? We chose this question, why does a balloon fly forward when the air is released from the back of it? The question directly relates to Newton's third law of motion. For every action, there is an equal and opposite reaction. The balloon's motion demonstrates this principle, making the question relevant and practical for understanding the law in action. In the balloon example, the action is the air rushing out. The reaction is the balloon moving in the opposite direction. So this question helps us understand the law in a real-world situation. By exploring this question, we can demonstrate how action and reaction forces pairs govern motion. It builds a conceptual foundation for more complex topics like propulsion in rockets and airplanes, and it also encourages curiosity and critical thinking through real-world explanation. Understanding this question helps us see how motion happens due to forces acting in pairs. It builds the basics for understanding how rockets launch, how birds fly, and even how swimming all works, all because of Newton's third law. Now, why did we choose this question? There were we chose some questions and then we rejected them. So we will talk about it. The purpose of this question. Our chosen question is, why does a balloon fly forward when the air is released from it? This question is designed to spark curiosity and facilitate a deeper understanding of Newton's third law of motion. By using a common phenomenon, it encourages students to engage actively with the material. It is simple, and at the same time, it is complex. For example, this question is clear and straightforward, making it accessible to a wide range of students. It encourages initial exploration of fundamental concepts. Well, despite its very straightforward in nature, the question invites deeper analysis of related concepts such as propulsion and momentum, providing opportunities for advanced discussions. We wanted to choose what is Newton's third law. The reason for rejection is this question is overly broad and may lead to generalized answers and do not encourage critical thinking or practical explanation. Or we wanted to choose how do forces interact. It is not specific and does not provide a clear context for investigation. Yes, when we were writing objective 4 and 5, because they're interconnected, it was hard to choose a question. There was some complication in question writing. Crafting and engaging in an educational question presents challenge. It was essential to ensure that the question aligns with the learning objective, which is Newton's third law of motion. The goal was to create a question that would not only prompt observation, but also encourage hypothesis-driven experimentation. We selected this experiment on the basis of the visual of action-reaction relationship. In this video, we are going to go ahead and demonstrate Newton's third law of motion. We ensured the question was open-ended to prompt explanation. It should be open-ended. It should not be closed-ended with yes or no answer. Rather than just recall, a balloon is easy to test and observe. The idea came from wanting a hands-on example that also sparks curiosity. I'm going to go ahead and play this video and demonstrate Newton's third law of motion with experimentation and visuals.
Hello, my name's Mike Diaz. Third law of motion, for every action, there's an opposite and equal reaction. So I'm going to blow the balloon up and attach it to the straw. And what's going to happen now is the force inside the balloon, the air that I just blew in the balloon, is going to be the force. So as that air and that force comes out of the balloon the back way, it's going to push the balloon forward. For every action, there's an opposite and equal reaction. Force comes this way, balloon goes that way. Similar to like when a rocket takes off. When a rocket takes off, the fuel, the thrust of that fuel coming out the bottom of the rocket allows the rocket to go straight up. Or like when an airplane takes off, the thrust of that plane coming out the back allows the plane to go forward. So same kind of a thing, picture this like an airplane. The engines are right here, forcing the air out this way, which will allow the balloon to go the opposite way. For every action, opposite and equal reaction. Here we go. And those are Newton's 3 laws of motion for a few moments in science. Thank you.
All right, here we demonstrate our experiment in objective 4.3. Compare and contrast the question to others found in textbooks. Yes, this question is unique. This question stands out because it employs a familiar object, a balloon, to illustrate a scientific principle. Unlike traditional questions often found in textbook, it emphasizes hands-on experimentation and practical application. Comparison, in the textbook, mostly the question is asked, explain Newton's third law. Limitations, often theoretical and detached from real-world application, may not engage students, or it didn't engage us meaningfully. Our questions is, why does a balloon fly forward when the air is released from it? The strength for this question is it encourages us or students to conduct experiments, providing a deeper understanding through direct observation and interaction with the concept. We took some extra step in finalizing our question. It includes additional components that are often lacking in standard textbook questions, such as encouraging students to record their observation. In the next slide, we will be able to show you that we record some observations and reflections during the experiment. We also prompt them to make predictions, or prompt our students or prompt ourselves to make predictions based on our understanding of action and reaction forces, enhancing critical thinking skills. And also, we already saw and demonstrate the balloon experiment in the video. This question connects theoretical principles to everyday experiences, such as rocket launches and vehicle motions. It also reinforces the relevance of Newton's laws in practical context, making the learning experience more meaningful and engaging. The question is unique. It covers our objective 4.4 because this question is unique. It uses a common and familiar object, a balloon, to explain a scientific idea. Most people see how a balloon moves when the air is released. They already have seen this, but they may not realize it's an example of Newton's third law. This makes the question interesting and easy to understand. It also allows us or students to test the idea themselves, which help them to see the concept in real world, live, not just in textbooks. Amy, you want to go?
All right, so objective 5.1, the example question demonstration and solving. So the diagram usually demonstrates Newton's third law of motion using a balloon as an example, and it includes two main parts. On the left, a hand is shown holding the inflated balloon just before it's released. This sets the scene for the motion that follows. On the right, the balloon is released and moving upward. Two label arrows illustrate the forces involved. So the top red arrow would be the reaction and the bottom blue arrow is the action. The text above the diagram reinforces Newton's third law with a clear definition. It reads, for every action force, there is an equal in size and opposite in direction reaction. All right, so 5.1 is going to be our graph or table. You can see that the balloon size in centimeters, and then the air pressure and the reaction force on air, and then the force on the balloon. How this chart was made, the force was calculated using force equals P times A, where P is pressure inside the balloon measured in kilopascals. A is the nozzle area assumed constant. For this demonstration, assume the area stays constant at 1 meter squared for simplicity. That way, force in newtons equals pressure. Why this helps, the table shows that increased air pressure inside the balloon leads to a stronger reaction force as the air is expelled, making the balloon move in the opposite direction. This aligns with Newton's third law. All right, and then 5.2 is going to be formulas and constants explanation. The key formula is force action equals force reaction. So F equals force in newtons. The negative sign indicates the direction is opposite. Units is newtons or kilograms times meter per second squared. The typical force values in balloon experiments range from 2 newtons to 15 newtons depending on the balloon size and air pressure. So the pressure formula is force equals P times A, where P equals pressure and A equals area. Pressure inside the balloon is what drives out the air and causes the forward push on the balloon. When something exerts a force in another object, that object pushes back with an equal force in an opposite direction. Applying it to a balloon, when you let go of an inflated balloon, it starts flying around the room. But what's really happening? The air inside the balloon rushes out. That would be considered the action. And the balloon flies in the opposite direction, which is the reaction. While Newton's third law is conceptual, we can represent the forces mathematically. Fair equals negative F times balloon. What does this formula mean? Fair is the force the air pushes outward, and then F times balloon is the force that the balloon is pushed backward in the opposite direction. The negative sign shows that these forces are opposite in direction but equal in size. And then visual analogy, imagine you're on a skateboard and you throw a heavy backpack forward. You'll roll backward. It's the same idea. If you're the balloon and the backpack is like the air being expelled. This illustrates how the force of the air escaping backward is equal in magnitude and opposite in direction to the force propelling the balloon forward.
Okay. How can we apply this understanding to different problems? We chose this problem. The balloon is inflated until the pressure inside is 9 kilopascals. The nozzle opening is 0 and 100 meters squared. What is the force exerted on the escaping air, and what is the force pushing the balloon forward? Now, the step-by-step solution. First of all, we know the pressure is 9 kilopascals, which is 9,000 pascals, and the area is 0 and 100 meters squared. We apply the formula, which is force equal pressure times area. So 9,000 times 0 and 100, which is 90 newtons. So we interpreted the results. The force on the escaping air is 90 newtons. By Newton's third law, the balloon is pushed in the opposite direction with the equal force, which is 90 newtons. We proved our step-by-step problem with this formula. Direction matters. If the air is forces backward, the balloon moves forward with equal magnitude of force. It completes our objective 5.3. Solving process thoroughly described. Yes, the balloon is inflated and then released. Air rushes out, which we have seen in the problem and the back of the balloon. This is the action force. When the air rushes out the back of the balloon, this is called action force, and the balloon moves forward in the opposite direction. That's the reaction force. According to Newton's third law, these forces are equal and opposite. Sorry. 5.4. This demonstration applies Newton's third law. It breaks down the concept into observable parts and shows the direct relationship between action and reaction forces. The diagram we can see, the question, the diagram, and the balloon's motion all help explain how force act in equal and opposite pairs. It fits the topic perfectly and makes the law easier to understand. Here is a little bit demonstration, or here is a little bit in the picture. We can see we verify accuracy and relevance by using the force formula and pressure formula. This concept perfectly aligns with Newton's third law, equal and opposite forces between the escaping air and balloon.
So in conclusion, the universal application, Newton's third law applies universally, whether objects are at rest or in motion. Force pairs, forces always come in pairs, known as action-reaction force pairs. Examples would be like walking, your foot pushes backward against the ground and the ground pushes forward. Another example would be rocket launch. The rocket engine expels exhaust gases downward and the gases push the rocket upward. Objective 6.1, additional interesting information. Isaac Newton is best known for his three laws of motion, but he also developed the law of universal gravitation, invented calculus, which we said earlier. He wrote the landmark book Philosophiae Naturalis Principia Mathematica. Newton worked with and was influenced by other great thinkers like Robert Hooke, Edmund Halley, and Christian Hughes. It took him at least 20 years of thought and refinement to publish his laws of motions. His discoveries still shape modern physics, engineering, and astronomy today. Some things in Objective 6.2 that surprised us would be Newton's third law applies even when objects don't move. How many everyday things like walking or swimming depend on invisible interaction of forces. If we had more time, we'd explore how Newton's law applied to sports or animal motion. Some suggested topics for the future would be the science behind friction and gravitational waves, inertia in real life situations, forces in space, how do astronauts move and work in microgravity environments. What we wanted to know more about would be how Newton figured out all this out without modern equipment, and how space travels use this law in extreme conditions like zero gravity. In summary, Newton's third law of motion states that for every action there is an equal and opposite reaction. The principle explains mutual interactions between objects and essential for understanding forces in various contexts, from everyday activities to advanced technological applications. These are some of the references and sources we used.
We use some websites. These are the websites which we use, and all the images are subject to copyright. But even though we mentioned some of the sources and references which we can take from, these are the references from slide 1 through 10. These are the websites we got our information from, and this is the continuation. And thank you so much.